In this next video, in our lectures on the S-block elements and its compounds, we're going to be looking at the hydroxides that are formed from group 1 and 2 elements and how stable they are and how they can be formed. So we're going to start by looking at the group 1 hydroxides. So if you remember from the previous videos, we said that group 1 metals react violently with water, and when this happens, they form the hydroxide and hydrogen gas. That's also shown in formula form here. And you remember that as we descended the group, the reaction got more exothermic and more violent. I put a link to a YouTube video in the first lecture that showed this. He put the first 5 elements of group 1 with water, and we saw that the explosions got larger and larger each time. Now, lithium, sodium and potassium are all less dense than water, so they'll react on the surface. And because that happens, there's an entertaining video here of stone skipping, so to say, with sodium. If you throw sodium, it will react with the water and then bounce up, and that continues. With potassium, that's where the reaction starts becoming violent enough and exothermic enough that the hydrogen produced will actually ignite and you can start getting fires. And finally, with rubidium and cesium, these are denser than water, which makes it almost more violent and more reaction. More explosive even, because they'll sink beneath the water and then there'll be an explosion. However, we need group 1 hydroxides and we use them quite regularly. Sodium hydroxide and potassium hydroxide are 2 of the most common bases that we use in the labs, research-wise, teaching-wise and industrially. So there needs to be a safer way, and this way is through the Chlor Alkali process, as it's called. And again, like with the production of the metals, this is done through electrolysis. So we can take sodium chloride solution. Sodium chloride, we were saying, was very easy to acquire. It is salt, it's in the sea, it's in salt flats. And we react this with water electrolytically. So this isn't just dissolving sodium chloride in water. It's actually putting a cathode and an anode in these to use electrolysis to split the sodium chloride, and this then forms sodium hydroxide and hydrogen and chlorine gas, which then leave. And these hydroxides are what's called deliquescent solids. So when we get them in the lab, this is what they look like. They're formed into pellets. Potassium hydroxide is exactly the same as this. They look like these little pellets, but very, very quickly this happens to them. And this is because they absorb water from the air, and the water that they absorb also dissolves them. So this is what the meaning of deliquescent is. And all the hydroxides of group 1 are like this. As I said, potassium hydroxide is another common one you'll come across. And as well as them all being deliquescent, they're all soluble in water. Obviously, if the water is absorbing, is dissolving them. If you put them in a beaker of water, they'll dissolve, and they produce a strongly alkaline solution. And this is because they fully dissociate. So in the same way that a strong acid is something that fully dissociates and adds H+ to a solution, a strong base is something that adds fully dissociates and adds a lot of OH- to the solution. And that's what these group 1 hydroxides do. Finally, when we're looking at the group 1 hydroxides, we should mention stability. So the only one of these that isn't stable, and by that I mean it decomposes when you heat it up, is lithium hydroxide. So if you take lithium hydroxide and heat it up, you'll get lithium oxide and water. Water in the form of steam, because this happens above water's boiling point. And you'll remember that this can also happen if we do this at cooler temperatures. If we take lithium oxide and put it in water, like in the last lecture, we actually form lithium hydroxide. Now let's look at the group 2 hydroxides, see how they compare. So with the exception of beryllium, very much the same as group 1, they all react with water to form a hydroxide and hydrogen gas. And this is shown in formula form here. The difference this time, and it's because of the oxidation state of the metal, is that these are OH2, whereas in group 1 they were just OH. And then this is because the metal cation, as we said in the first video, of group 2 likes to be in a 2+, and OH is only a single minus charge. Again, just as in group 1, as we descend the group, the reaction becomes more vigorous, and these hydroxides are also basic. They're sparingly soluble in water this time, and what that means is that, yeah, unlike the pellets, you can't just chuck loads in and they will carry on dissolving. They aren't so soluble, but this solubility does increase down the group. And there's a couple of uses of these hydroxide solutions in water. The one I've got shown here is one we did a lot in the teaching labs when I was a student. I don't know if it's the same here, but it's a test for CO2. So if you put calcium hydroxide in water, which is also known as lime water, and bubble CO2 in it, it ends up turning cloudy. And this is because it reacts and the CO2 replaces the OH, and you get calcium carbonate, which is insoluble. Another use for these group 2 hydroxides is an example of magnesium hydroxide, and this one is commonly called milk of magnesia. And yeah, you can get this at the pharmacy. No, that's rubbish. It's an antacid, so it sort of neutralizes the stomach acid. Finally, let's take a look at beryllium hydroxide, because I said that was an exception, and then the stabilities. So beryllium hydroxide is different in that it doesn't react with water. You can't just put beryllium metal with water to form the hydroxide, but you can still form beryllium hydroxide. This time what you need to do is take beryllium chloride and react that with OH ions. So OH ions typically indicate a base, so yeah, from a strong base in solution. And then in this case, the OHs displace the chloride ions, and you end up with a beryllium hydroxide and chloride ions in solution. And beryllium hydroxide is amphoteric in nature, as opposed to the rest of the group 2 hydroxides, which are basic. And amphoteric means that it shows both basic and acidic properties. So it will react with an acid, much like you'd expect a base to. But if you carry on adding base to a solution of beryllium hydroxide, you get a complex being formed. So it'll also react with more base. Finally, the stability of group 2 hydroxides. They're less stable to heating than the group 1 hydroxides. So this time all of the group 2 hydroxides, when you heat them, will decompose to form the oxide and water in the form of steam.